In the last lesson and chapter in your textbook, we talked about light as a ray. That light has an origin and a direction associated with it. And we looked at how those rays pass through lenses and bounce off of mirrors. We're now going to look at light in a different aspect. Light, if you recall, is an electromagnetic wave. It's an oscillating electric and magnetic field, and as such, as a wave, it has a wavelength and a frequency. You might want to recall or move back to the last class, Physics 141, the first semester physics course. Toward the end, we had a topic or discussion on wave theory, or you can look at your book at those sections about waves. Longitudinal waves, transverse waves, which electromagnetic waves are, transverse waves, and how waves work, as a reminder if it's been a little while. So, for light, the speed of light, c, is equal to the frequency of the light times the wavelength of the light. Now, in a vacuum, the speed of light is exactly 299,792,458 meters per second, by definition. So if you know what the frequency of light is, you can calculate its wavelength. And if you know what the wavelength of light is, you can calculate its frequency in a vacuum because you know the speed of light. So if you're in space and you're listening to the International Space Station, you're listening to, for WASA, NPR, 90.9 megahertz FM channel. Well, the frequency is 90.9 million hertz. I can calculate what the wavelength of that light is using the speed of light equation here. Now, when light travels through a medium or material that's transparent, its speed slows. We talked about refraction and how and the index of refraction of a material. How much the light slows depends on that index of refraction. A diamond, which has an index of refraction of around 2.4, slows light considerably compared to glass, which might be around 1.5, or water, which is around 1.33. Interestingly, while the speed of light slows in a medium, its frequency doesn't. The frequency of light doesn't change. So when light strikes, if you have an aquarium at home, if blue light of a certain frequency hits the aquarium glass, as it moves to the glass, its frequency stays the same. As it moves into water, its speed changes, but its frequency stays the same. As it moves back into the glass on the other side of the case, its speed changes again, but its frequency remains the same. And then finally it gets back into the air, its speed changes, but its frequency remains the same. Well, frequency is remaining the same and the speed of light is changing, then the wavelength has to change. So what happens with light, effectively, is when light passes through different material of a different index of refraction, its wavelength changes. And since the speed of light in a vacuum is as fast as it can be, c can only get smaller when it moves through a material with an index of refraction greater than 1. So the wavelength must get also smaller or shorter. Figure out how much shorter, use the following equation. Right? The wavelength in some material, like diamond, for instance, or glass or water, is equal to the wavelength of light in a vacuum, which you can use this equation to calculate what that wavelength is, divided by the index of refraction of that material. So you can calculate what the wavelength of, let's say blue light, 400 nanometer light in a vacuum, what would it be, what would the wavelength be if it were as it passes through a diamond? Now remember, once it emerges from the diamond back into air, it speeds up again, and the wavelength goes back to close to what it was for a vacuum, because air has an index of refraction very close to 1. So light travels at different speeds in different mediums. As soon as it leaves the medium and enters the next medium, it immediately changes speed. It can speed back up or slow back down, but it can never exceed this cosmic speed limit. And likewise, as soon as it leaves or enters a medium, its wavelength changes. How much it changes depends on the index of refraction of the medium, and this equation gives you that relationship. So you can change the wavelength of an object. So for example, if you have two light waves, and they're in phase with one another, meaning that the peaks occur at the same location, the troughs occur at the same location, at the same time, these two beams of light are in phase. However, if I place some material, let's do a third beam of light, it has to go through some transparent material, glass, for instance. Let's say that it starts off in phase. The peaks occur at the same location. But now we're in an index of refraction. Let's say this is a chunk of diamond, right? Some transparent cylinder of diamond that I can make magically. What's going to happen now is the wavelength will change. The wavelength will get shorter. So the wavelength will get shorter. So when the light emerges, that didn't quite work the way I wanted it to. Let's change this a bit. So when the light emerges, as wavelength comes back, didn't quite work out the way I wanted to. This is a little bit more difficult. So it comes back. You can see that it's no longer in phase. So by placing an object through a different material, you can change the phase, and then of course its wave properties means interference can occur. And we talked about destructive and constructive interference. We talked last semester again about musical notes. We talked about harmonies. We talked about interference patterns for waves. So waves can interfere with one another, and this is a way that you could actually create constructive or destructive interference with waves, which becomes important, and we'll talk about that in a bit.